Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing single-phase full-wave controller with common cathode configuration. Why am I calling this as common cathode configuration? If you see here, T1 and T2 cathode both are connected together. So that is the reason we call it as common cathode configuration. And here this serves the similar purpose of single phase full wave controller. So here we are making use of four devices, namely T1, T2 and D1, D2, out of which two are thyristors and other two are diodes. Half of the devices are controllable devices and other two are uncontrolled devices. And here during the positive half cycle, here if you see during the positive half cycle, T1, D1 are forward biased, whereas during the negative half cycle, if you see, D2 and D1 are, during the negative half cycle, T2 and D2 will be forward biased. T2 and D2 will be forward biased. At a time, two devices will be conducting during the each half cycle. Here, since we are making use of four devices, the control circuit will be a bit complex, and apart from that, because of the high power dissipation, the efficiency will be getting reduced. So this is the disadvantage associated with the circuit. Or otherwise, let us check out the waveform and the circuit operation. See, during the positive half cycle, the polarities across the circuit will be positive, negative. Because of such kind of polarities, see, anode of the thyristor is more positive with respect to cathode, such that T1 during the positive half cycle, T1 as well as D1 will be forward biased. And here D2 and T2 will be reverse biased, and these two will be acting as off switch. So that is the reason here during the positive half cycle, T1 as well as D1 starts conducting current through the load. And this is the individual circuit diagram during the positive half cycle. And the moment during the positive half cycle, since T1 and D1 need to conduct together, the moment when we only provide the triggering pulse, the device starts conduction, otherwise no. And if you see, this is at the instant called zero crossing, positive half cycle has been appeared. But the moment when we provide the triggering pulse for the thyristor 1, when we provide the gate triggering pulse for the thyristor 1, only in that case, the devices in the positive half cycle starts conducting. So this instant, this is the output voltage here I am indicating, and output voltage starts appearing across the load right from the instant called alpha. The moment when I provide the triggering pulse, only then thyristor starts conducting. So here T1 and D1 are conducting at once. So right from this instant called alpha, T1, D1 started conducting, and how long it is conducting till pi. And the moment it reaches pi, what happens? Supply voltage is becoming 0. That is how T1 and D1 are now turned off, and at this instant negative half cycle has been appeared. Supply voltage will be negative now, and due to which the polarities will be again now negative, positive. And because of such kind of polarities, now T2 and T2 will be forward biased. So the moment when we only provide the triggering pulse, T2, D2 starts conduction. So here, the moment when we provide the triggering pulse at this instant called pi plus alpha, we have provided the triggering pulse for the thyristor 2. So this is Ig2 I'm indicating, and the moment when we provide the triggering pulse, that is the instant called pi plus alpha. At pi plus alpha, we have provided the triggering pulse for the thyristor 2, and now thyristor 2 started conducting current through D2, supply and load. So this is how we are getting the output voltage right from pi plus alpha to 2 pi. And if you see during the positive half cycle, the current through the load will be See, through T1, D1, load and back to supply. This is the direction of the current flow through the load during the positive half cycle. Whereas during the negative half cycle, if you see, the current through the load will be flowing through T2, D2 and back to supply. And if you see, the current direction is now flowing in the reverse direction to that of the first case. This is during the positive half cycle and this is the individual circuit diagram during the negative half cycle. And if you see, current flow is from A to B during the positive half cycle, whereas current flow in the negative half cycle is right from B to A, which is exactly reverse to that of the first case. That is the reason here in AC voltage controller, both positive half cycle of the supply voltage as well as negative half cycle of the supply voltage will be controlled, and that is how we are getting AC output. Whereas in rectifiers, irrespective of the current flow through the supply, the current flow through the load will be unidirectional. That is how we are getting DC over there. Whereas here in controllers, AC voltage controllers, because the output current is reverse in both the cases during the positive half cycle as well as negative half cycle. That is the reason here we are getting output as AC, bidirectional control. So here during the negative half cycle, T2 and D2 are conducting. T2 and D2 are conducting right from this instant called pi plus alpha to 2 pi, and the moment it reaches 2 pi, supply voltage is 0, and again positive half cycle is again appeared and cycle repeats. So during positive half cycle, T1 and D1 will conduct, whereas during negative half cycle, T2 and D2 will be conduct. And as I told you, here in AC voltage controller, output current will be equal to that of the supply current. I0 is equal to IS, and both the waveforms will be similar because same path, same current is flowing through supply as well. That is the reason here I0 is equal to IS, and it is conducting from alpha and again till pi, T1 D1 conducting, and again from pi plus alpha to 2 pi, T2 D2 conducting. So that is how we are getting output current, which is just similar to that of the output voltage. And this is the waveform for the current through the thyristor 1. And if you see current through the thyristor 1 as well as this is the current through the thyristor 2. See, current through the thyristor 1, when it is conducting from alpha to pi, we are getting the waveform for the current through the thyristor 1. And this is the current through the thyristor 2. And this is the waveform which is actually present right from pi plus alpha to 2 pi only when the thyristor is conducting current through the load. Again, the cycle repeats. Let us see one more configuration, how we can actually achieve this bidirectional control. Previously, we have seen one of the configuration that was common cathode configuration. Now, this is single phase full wave controller with bridge configuration. That is, here we are making use of a bridge configuration with one additional SCR. In the circuit, if you see, here we are making use of 4 diodes and 1 SCR and 1 SCR. So if you see, here SCR will be turned on during the any half cycle of the supply voltage. During the positive half cycle as well as negative half cycle, T1 remains turned on. So here T1 is on in both the cycles, and at a time 3 devices will be turned on. So how about turning off of the thyristor when it is conducting in both positive half cycle as well as negative half cycle? When the supply current goes through 0, at that instant thyristor will be turned off, and again the moment when we provide the triggering pulse, T1 starts conducting. This is fine with a resistive load. But what if we are making use of inductive load? If we are making use of inductive load, in that case, there is no way thyristor cannot be turned off. It will have to conduct continuously because of the energy present in the inductor. So in that case, control will be lost. So this is the disadvantage associated with this particular circuit. And here if you see, at a time 3 devices are turned on. Two diodes will be conducting and one SCR will be conducting. And in that case, what happens? Power dissipation, that is power loss, will be more and efficiency will be getting reduced. And apart from that, here we are making use of so many devices. The control circuit will be a bit complex. So these are the various disadvantages associated with this particular circuit. And if you see, let us see the circuit operation firstly. During the positive half cycle of the supply voltage, see here D1, let me write down here. During the positive half cycle, if you see D1 as well as D2 will be turned on and it will be conducting current to the load. Whereas during negative half cycle, what happens is D3, D1 as well as D4 will be turned on. So here during the positive half cycle, if you see, when the polarities are positive, negative, because of which, see, D1 is forward biased and it will conduct T1 and as well as D2. So the circuit, individual circuit will be like this: T1, D1, T1, D2, load. Now current is flowing through the load and then back to supply. This is how current flow through the circuit during the positive half cycle will be. So here during positive half cycle, the moment when I provide the triggering pulse for IGT1 at instant called alpha, what happens? I am indicating here the output voltage, where output voltage is equal to I naught into R. The moment when current is flowing through the load multiplied by load resistance is nothing but your output voltage, where output voltage is equal to, it is actually appeared across the load right from the instant when we provide the triggering pulse for the thyristor 1. So here T1 is conducting, D1, T1, D2, D1, T1 and D2 are conducting right from alpha to pi. And the moment it reaches pi, supply voltage is becoming 0. So negative half cycle will be appeared, and because of which polarities will be reversed. So that is the reason here T1 will be turned off and it remains off for some period of time. And when now during the negative half cycle, the polarities will be negative, positive, and because of such kind of polarities, here D2 will be forward biased, here D3 will be forward biased, T1 will be forward biased, as well as D4 will be forward biased. So what? It starts conducting current through the load in this direction. Now current is flowing in the upwards direction because of D3, T1 and D4, opposite to that of the first case. That is how we are getting the output as AC, as I told you previously. So here now right from this instant called during the negative half cycle, at this instant called pi plus alpha, since we are providing the triggering pulse at pi plus alpha, here D3, T1, T1 and D4 are conducting, and it is conducting till 2 pi. Output voltage will just follow the input voltage, supply voltage waveform till 2 pi, and the moment it reaches 2 pi, what happens? Positive half cycle will be appeared, and because of which T1 will be turned off. All the 3 devices will be turned off and it remains off for a certain period of time, and again it is on. So the cycle repeats. This is the output voltage waveform. Coming to the output current is just similar to that of the output voltage waveform. And if you see here, the same current, same current is flowing through the supply as well because of the same path. So that is the reason here I naught is equal to Is. And if you see, output current waveform will be just similar to that of the output voltage because of the resistive load. Only the magnitude will be reduced when compared to that of the output voltage, or otherwise output waveform will be one and the same. So that is the reason here from alpha to pi, we are getting the output current waveform and it is becoming 0. And again here we are providing the triggering pulse for the other 3 devices. That is how they started conducting, and again off. Cycle repeats. This is the waveform for output current or supply current. Talking about the current through the thyristor 1. So here current through the thyristor 1 is present during the positive half cycle as well as during the negative half cycle, because thyristor 1 is conducting in both positive as well as negative half cycle. As I told you, this is the disadvantage because it is remaining off only for a certain period of time. And what if you make use of inductive load? It will never turn off and control will be lost. So, and one more thing, here we are making use of 3 diodes. 3 devices will be on at a time, 2 diodes and 1 SCR. At a time, 3 devices are conducting, which are contributing to the power loss, and because of which efficiency will be getting reduced. And coming to the advantages, if you see here, input current waveform, output current waveform, as well as output voltage waveform are symmetric. So, because of the symmetric waveform, DC component will not be present, and because of which saturation of the transformer will not take place, and at the same time, saturation of the loads will not take place. So, that is the advantage. And coming to the disadvantage part, here control circuit is complex. That is the disadvantage associated with this particular circuit, because here we are operating more number of devices and control circuit will be a bit complex. And coming to the application part, here we'll be making use of this controller in induction motor pumps as well as fans. And if you see, this is the individual circuit diagram during the positive half cycle, and this is the individual circuit diagram during the negative half cycle. This is the individual circuit diagram during the negative half cycle of the supply voltage. So this is all about the various configurations instead of single phase full wave controller. That is, we have common cathode configuration and other is bridge rectifier with 1 SCR. And in the coming lecture, we'll be seeing single phase full wave controller with inductive load. Thank you.